We're not going to get into much details of the organic chemistry itself. We're going to go over just how to look at molecules, what is organic chemistry, and what are the most important functional groups in organic chemistry. Now, when I started taking organic chemistry, when I first took organic chemistry, my professor told me a story. Now, organic molecules, right? Organic chemistry is the study of carbon-containing molecules. Now, in the past, organic molecules were known to be any molecule that comes from living beings. And they said that we cannot form and we cannot create organic molecules in the lab. For the longest time, they said we could only form non-organic molecules, but organic molecules needed a living being to put energy into it and form these organic molecules. So organic molecules were known to be off limits. No one tried to produce them. They said you cannot produce them in the lab. They can only be produced inside a human body or another animal. It has to have that life essence, they used to call it, right? It has to be from a living organism. Eventually, there was one of the scientists, they're always doing experiments. He added two chemicals together and he let it run overnight. And he's in the lab, a lot of people in the lab, everyone doing their own experiments. He added a few things together and he let his reaction run overnight. He comes back the next day and he tests his beaker. And he finds that he has urea. Do you guys know where you find urea? He found urea, which is an organic compound, which cannot be synthesized in the lab. It has to come from a living body. And urea is the main component in our urine, in our pee. So, he thought someone's playing a dirty joke on him, and his lab mates came and peed in his reaction mixture. So he got angry, he got furious, he went around asking everyone, so who's playing the dirty joke on me? Please let me know. Please, who peed in my mixture? Everyone's like, no, it wasn't us, it wasn't us, it wasn't us. And he's like, okay, that's fine. Let it go. I'll do the reaction again. So he ran the reaction a second time. Once again, left it there, left it overnight, came back, and he finds urea. Now he's furious, right? He's like, who's messing up my experiment? And who's playing this dirty joke on me? So eventually, everyone denied it. Everyone said, we are not the ones doing anything, right? It's not us. So this time he said he's gonna sit there the whole night. It's a long reaction. So he ran the reaction, he sat there the whole night to make sure no one is doing anything with his reaction mixture, and eventually, once again, he found urea. That was the first time an organic molecule was synthesized in the lab, which was previously known to be impossible. Now, this is the story that I was told. Later on, I went to try to search for the story. There's a bit of a discrepancy in the story. It might not be a true story, but either way, it is kind of something interesting. But urea was found by accident. And that was the first organic compound that was synthesized in the lab, and that broke the barrier that people thought was impossible. Right? People were like, we're not even going to try to synthesize organic molecules because it's impossible. But once they found out that it's possible, everyone started creating new organic molecules in the lab. And eventually, they found out how to make all the different types of organic molecules, and they came up with a whole different type of science called organic chemistry. Now, eventually, now we know organic chemistry specifically relates to carbon-containing molecules. But the reason why this is important is because every single living being is made up of a lot of carbon. And what happens is the carbon is cycled throughout the world, throughout the universe, right? Throughout our planet, carbon is constantly circled throughout all the different living organisms that are present, right? So that is important to have chemistry, that's carbon, and understand why carbon is so interesting. So just a few things to remind you about what carbon is so that we can see why it plays a specific role and it has a specific attributes in organic chemistry. Now, nonmetals share electrons through covalent bonds, right? We know that. A pair of covalently bonded electrons, right? We know that as a bond. And then you have lone pairs of electrons. That's how we draw our Lewis structure. If you have a look at the non-metals in our periodic table, those are the ones that are going to have covalent bonds. In general, right, hydrogen has 1 valence electrons, carbon has 4, nitrogen 5, oxygen 6, and fluorine 7. Therefore, in order to satisfy the octet rule, hydrogen needs 1. Therefore, it will form only 1 covalent bond. Carbon, or fluorine, needs 1. It will form 1 covalent bond. 2 for 2, 3 for 3, and carbon has 4 valence electrons, needs 4 more electrons, and therefore will form 4 covalent bonds. That is important for us to understand what we're going to be drawing and what we're going to be looking at when it comes to carbon. And these 5 compounds are the most abundant compounds in organic chemistry. Mainly, these are all the ones that you're going to be dealing with. Very rarely you're going to be dealing with anything other than this. Sometimes some chlorine, sometimes some sulfur. But organic chemistry, most organic molecules, right, are made up of these 5 different compounds, which is connected in different ways. And when atoms are connected in different ways, it changes the attributes and characteristics drastically. Now, those are the important ones. As you can see over here, first one is natural gas, right? If you have a carbon connected to 4 hydrogens, this is something very useful, right? We burn it all the time, right? If you have a gas stove at home, this is what you are burning, methane. If I take out 1 hydrogen and I replace it with a nitrogen with 2 hydrogens, it changes from something which is natural, right? Something we can burn all the time, to a really stinky, right? Foul smelling gas that is formed from a decaying fish, right? So this change of the hydrogen to a nitrogen changed it from something that will burn to something which smells horrible. I take that same compound, C, with 3 hydrogens. Instead of the nitrogen, I'm going to connect a oxygen this time. And now that is known as methanol. Right? Very important solvent that is used in multiple different industries, specifically perfume industry. And a lot of different industries, they use significant amounts of methanol. So a small change from a hydrogen to a nitrogen to an oxygen can cause varying, drastic changes in the properties of these compounds. That's why organic chemistry becomes very interesting and fun to learn. Now over here we have different types of organic compounds, right? For example, we have ethylene over here, acetylene, we have formic acid, we have hydrogen cyanide, and as you can see in every single one of them, if you look at the carbon, it has 4 covalent bonds. Oxygen will always have 2 bonds, hydrogen will always have 1 bond, and nitrogen will always have 3 bonds. Okay, now we're going to take that as a rule for OChem. It's always going to be like that. Remember when we were drawing Lewis structures, we said not always, right? For OChem, it's pretty much always going to have and follow that specific rule. Okay? Now, sometimes you can have different arrangements of the same molecule. For example, if I tell you to draw C3H7Cl, right? We said C3, so we have 3 carbons. We have 7 hydrogens. But in this one, we put the chlorine on the middle, and this one, we put the chlorine on the right side. These 2 compounds have different properties. They are not the same compound. They have different melting points. They have different boiling points. They are what we call isomers. Isomers are compound with the same molecular formula, but different bonding arrangement. That means they are rearranged and connected in a different way. And that will change their properties. Okay? Yes?
How do we find these arrangements? How do we find these arrangements?
How do we find these arrangements? We made them. Right? So either we're synthesizing them in the lab, or we find these two compounds in nature, and then we study them. We're like, wait a second, they have the exact same molecules, the same atoms, but then when we study them in detail, we find that they have different arrangements. Right? So they are known in nature as two different compounds. And when we study them, we see that they are different. Or we synthesize them like this in the lab. Eventually, if you guys study advanced organic chemistry, the whole purpose of organic chemistry is all about the different types of reactions, and for you to be able to synthesize any organic molecule you want. After studying advanced organic chemistry, you'll be given a starting molecule and an ending molecule, and you should be able to figure out how to get there, regardless of how many steps there are. Right? If you guys remember, some of you guys I told you, when I was taking advanced organic chemistry, that's when Breaking Bad came out. Okay? And I went online, me and my friend went online, we looked for the chemical formula for crystal meth, and we started with a specific molecule, and we wrote down step by step how to synthesize crystal meth. Right? That's what we were doing, right? Breaking Bad was pretty big at that time, and that's what we were actually synthesizing. We actually sat down and wrote it down. And then when you watch the show, some of the experiments that he's doing is like, man, I know what experiment he's doing. Right? Some of them is pretty legit. Right? So they tried their best to make it as close as possible to reality, but not all of it you can do. Some of them you need high pressure experiments. Anyways, but that's the beauty of organic chemistry. Organic chemistry is one of those subjects that people are very, very scared of. I loved organic chemistry. It was actually one of my favorites, but it was still hard. I'm not denying that it's hard. There's a lot of things to memorize. Where are the reactions going to go? What's going to attack different molecules? You're always looking at reaction mechanisms. But from the beauty of the chemistry itself, being able to synthesize anything you want made me really enjoy it. And specifically, OChem Lab is really fun because you're synthesizing some very important molecules, and sometimes you're synthesizing things that you use on a daily basis. Right? So there are some good experiments that you're going to do. Some of the synthesis that actually we do is actually smells. Organic chemistry has some beautiful smells. We'll go over a few of the molecules in a bit, right? So there's like the cinnamon smell, the vanilla smell, all the different flavors. All of these synthetic molecules is all from organic chemistry. Anyway, so isomers, as we said, are different arrangements of the same atoms. They have different properties from each other. But if I took that chlorine and moved it to the left side, would that also be a different isomer or not?
No.
Why not?
Symmetry is the same?
Huh?
The symmetry is the
Symmetry,
same?
right? You guys gotta realize all of these bonds can move. So if I take this molecule as a 3D molecule and flipped it around, it's still the same molecule. Right? So if I put the chlorine on this side, it's still the same molecule. If I put the chlorine on the bottom, it's still the same molecule. Right? Bottom on the left, same molecule. If I put it on the right, as well, same molecule. What matters is which carbon it is connected to. And when you get into naming, you're going to start numbering the different carbon atoms. For example, like this one. So here we have 4 different molecules. Now, if I look at this one and this one, are they different from each other? Are the top 2 different from each other? They both have chlorine connected to carbon number 1, which is at the edge. They're not connected to the central carbon. So therefore, those are the same. What about this one here?
Yeah.
Is it still the same? Yes. What about that one over there? Is it still the same?
No.
Yes. You can orient every single bond in whichever direction you want. What matters is how they are connected. All four of these are not isomers of each other. They're the exact same molecule. An isomer is when it's a different molecule that you cannot make just by reorienting everything. It has to be breaking a bond and moving it somewhere else. So these four are not isomers. Okay, they are the exact same molecule. Whereas in the previous one, these two were isomers. They're different molecules with different properties. Okay? Now, there are two isomers that have the molecular formula C2H4F2. Draw the Lewis structure for each of these molecules. So, when you're asked to draw isomers, you have to draw two different molecules. So, let's go ahead and start drawing it. Carbon is going to be in the middle. I have 6 bonds, right? I have 4 hydrogens and 2 fluorines. Where should I put the fluorines? And where should I put the hydrogens? Any ideas? Yeah. One on the right, one on the left. Okay. So let's put a fluorine over here. Top is fine. Okay, there we have one molecule. Now, second one. Where do I have to put the 2 fluorines?
Both on one side.
Huh?
Both on either left or right.
Right, both on the same side. Right? These are 2 different molecules. In reality, one of them is polar, one of them is actually non-polar. Right, slightly. But you'll get into that later on. What if I had this one? Is this also an isomer?
No.
Connected differently, right? Yeah? Keep in mind, that one is, as you said, the same as the first one. Right? Regardless of where they're connected, they're still connected to 1 fluorine to each carbon. That last one and this one are exactly the same molecule, so therefore this is not an isomer. There are only 2 possibilities. Does that make sense? It's good to practice these, because in OChem, this is a lot of what you're going to be doing is this. Trying to combine different atoms to the carbon to make a different structure. Okay, those are our 2. Yes?
Okay, so to be clear, an isomer is one that is not the same, right?
Yes, an isomer when they are not the same molecule. They are 2 different molecules and different properties. But they have the same formula. Right? They have the same number of atoms in the molecule, but they're connected differently. Okay? Now, the question says to draw 3 isomers for C5H12. This time I only have carbon and hydrogens, and I have to draw them in 3 different ways. First one is obvious, right? First one is easy. We're just gonna connect carbon, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. I'm not gonna write all the hydrogens. So this is our first isomer. Is there any other way that I can connect 5 carbon atoms? Huh?
In a circle.
Make it a circle? So you're saying like carbon, 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 carbon. Like that? Okay, so if I have 5 carbons here, each carbon has to have 4 bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can't have 12 hydrogens. So that's not gonna work. Right? I have to have, that's a good idea. We'll get into those later, but right now, we can't do that. Okay? Any other ideas?
Connect the carbons in like squares? Like,
Huh?
like a grid of carbons?
A grid?
Like a cube, like two carbons and then two carbons, and then they're like,
Once again, another square?
oh god.
You're saying like this?
and then put
And then another carbon? Okay, let's see if we can add our 12 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Can't put 12 hydrogens. Yes.
Get rid of one of the bonds between the two carbons. Right? Wait, no, that makes the same thing. Never mind.
Oh wait, why don't we just do carbon and then 4 around?
Wait, what did you say?
I said draw that again, but get rid of one of the bonds
Okay.
between.
So you said do this, 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 and this?
Yeah.
Can I get 12 hydrogens with that? Let me just rearrange that a little bit to make it look nicer. Right, if you have 4 in a line and 1 branched out, I will get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That is my second isomer. 4 with 1 branched out. It's a completely different molecule. Any other possibility? We need a third one. Yes.
You could have 1 carbon and then 4 carbons attached to it, surrounding it, and hydrogen on the surrounding.
There we go. I have a carbon in the center with 4 carbons around it. Or you can say I have a line of 3 carbons with 2 of them branched out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Those are our 3 different isomers. Now you can imagine, this one is only 5 carbons, and I have 3 different isomers. If I have 4 carbons, if I have 5 carbons, if I have up to 10 carbons, there are so many different type of isomers and different connections that you can have. Every single one of these molecules will have a different property, different melting point, different boiling point. Okay? So that's what makes organic chemistry the huge science that it is by itself. So there we go. We have 3 different isomers for our C5H12. These are the 3. Either they're all connected in a line, or we have a branch, right? 1 branch out. We have a line with 1 sticking out, or we have a line with multiple sticking out, or in this case, it is a central carbon with 4 carbons around it. Now, when we're drawing these structures, sometimes these structures get really, really annoying to draw, and they get really big. And we know we're always going to be using carbon, so we've come up with a shortcut. There are different shortcuts that we use. Instead of using, right, the normal Lewis structure that we know of, sometimes now we're going to start ignoring the lone pairs. They're obvious. We know that oxygen will always have 2 lone pairs and 2 bonds. Carbon will never have a lone pair. So we usually do what is called a condensed structure. And one of the labs, you kind of got introduced to this a little bit, where if I have this molecule, I condense it down, and they're listed in the order of their connectivity. So the first carbon has 1, 2, 3 hydrogens. So I call that CH3. Then I have CH2, CH2, and then CH3. This is what we call the condensed structure. From this, you know how they're connected, so you should be able to draw this. Now to simplify it even further, what we do is those 2 in the middle, since they're exactly the same, right? They're the branch, right? They're the middle part We combine both of them in brackets, and we just put a 2 next to it. Okay? So those are our condensed structures. Yes?
How would you do a condensed structure for something that doesn't look as linear as that? So, like one of the
Next example. That one.
yeah.
Right? So you have to look at each carbon and write down everything that's connected to that carbon first. And you're going to go in order. So the first one is CH3. Second one we're going to say is C with only one hydrogen. And then before writing the third carbon, we're going to say that carbon is also connected to NH2. So the emphasis is every single carbon. We have to go in order of carbons and write down everything that's connected to that carbon before going to the next carbon. So that's why we have CH3, we have CH, and then we have NH2, and we know that that is connected to the carbon that was right before it. And then we have a CH2 and a CH3. These are our condensed structures. Does that make sense?
Do you condense the CH3 too, or is it just you have to like fit one out?
Which ones? The ones that are on the sides?
Yeah.
Because they're not connected to each other, you cannot condense them. You cannot put them in a bracket. You mean put them in a bracket and put a 2?
Yeah.
No, they're too far away from each other, right? We have to go in order of how they're connected. Right? So in that case, if they were close to each other, there's CH3, CH3, then yeah, you can put CH3 twice.
So it's only if they're connected when you like condense it.
Yes. You have to go in order. Right? But when you say condense it, this is already condensing.
Yeah.
But you can't put them in brackets and put a 2. Right? Unless you have the repeating structures. Does that make sense? Is that good? Okay. Now, over here, how would we condense this one? Right? How would you condense this one?
Which one is the first C?
Huh?
Which one's the first C?
Which one is the first C? Which one is the first carbon?
The H3C.
But they're all
Right, so don't only look at the ones in the middle. Right? Now, the longest possible carbon chain in this specific molecule is how many carbons?
So 4.
4. Right? I can connect 4 different carbons to each other. So that means the base molecule for this compound is going to be 4 carbons. And now I have to start numbering them. So if I number them, right, I'll do it the right way. 1, 2, 3, 4. Now, I could have chosen 1, 2, 3, 4. That's also perfectly fine. Right, now if I took 1, 2, 3, 4, you'll study later on why that would actually be wrong. Right, but we're not going to deal with that in our class. Anyways, the idea is you have 4 carbons. So if I'm going to start condensing them, or just for the sake of comparison, or just to make it easy for us, since we're going from left to right, let's continue from left to right. So I'm going to say I'm going to start over here, 2, 3, and 4. So I'm going to say this is CH3. This is CH. Right? The second one only has 1. The third one has C without any hydrogens. But then it has a CH3, so I'm going to put that in brackets connected to it.
And then subscript 2.
And then I write down the 4th carbon, which is also CH3. Okay? Yes.
You couldn't say for the one with the brackets, you couldn't put a subscript of 2 because they're both CH3.
What do you mean? So you're saying put this as CH3 with the subscript 2?
With the 2, yeah.
Now, that should be fine because you can say there are 2 CH3s connected to this carbon. But if you want to continue your numbering scale, you have to show that this CH3 is different from this CH3. Because usually when you put the bracket, you can kind of say they're connected to each other. Right? So if I say CH3, I'm saying these two CH3s are connected to each other. But in this case, they're not.
Yeah.
Right? So it changes. So that will confuse people. Okay? Okay. Anyways, don't get too worried about the structures and the condensing and all that stuff. We're not going to be focusing on that too much. But you should know how to do that. Now, okay, so for here, we have two condensed structures. I want you guys to draw. So we'll go ahead and draw the simplified Lewis structures for each of these condensed structures. And we don't have to share the unbonded, unshared electrons. So first thing we're going to start off with is CH3. I'm not going to draw the hydrogens. What is that connected to? An oxygen. Then what? Then that oxygen is connected to a carbon. What does that carbon have now? It has a hydrogen. And in this case, what you were saying earlier, they did that condensation and they put it in brackets, so we have two CH3s. So I have a CH3 over here, and I have a CH3 over here. I cannot have a CH3 and then connect another carbon over there, because CH3 means all three spots are taken, and carbon cannot have another bond. Okay? You can move it around a little bit. You're looking at the answer in the next slide?
No, like I'm looking at it. Oh, it's right there, huh?
Okay. The answer is in the next slide, where we have it like that. Okay, anyways, that's what we have. Now let's go ahead and do this one. Right, the reason this is connected on the left, because it is going to be on the left, we're going to say an OH is connected to a carbon. That carbon has two hydrogens. Connected to a carbon, has one hydrogen. Since it's in brackets, it's connected to the carbon that's before it. So I have a CH3 over here. Then what do I have next? I have a nitrogen. What's on the nitrogen? Nitrogen has one hydrogen. Then where's the carbon? Carbon, two hydrogens, carbon, two hydrogens, and then we have OH. So from the condensed, it's easier to go to the structure. Okay, so make sure you guys go through the homework questions. The homework questions are not that long for these last few chapters. They are very, very short. So make sure you go ahead and do their homework assignments. You will practice this a bit in the homework.
Don't skip. No.
Now, even this condensed structure
It's wrong.
gets too long and too time consuming for organic chemists to draw. So we've even simplified it even further. Right, those are our answers. Now we simplify them further into what we call skeletal structure, where we stop writing carbons and we stop writing hydrogens. All we do is lines. Okay? Yes.
Double bonds.
We'll go over that.
Little
So,
mini lines.
we have two structures right here. This is the skeletal structure for two organic compounds. Every single, what do you want to call this? Like a point, an axis,
Yeah.
a turn, right? That represents a carbon.
The line.
Every time there is an angle, there's a change of direction, that represents a carbon. So over here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 carbons. Even that line sticking out is a carbon.
Honestly, seems
Okay? It's a lot easier because we have long, huge compounds, and we're only representing the bonds. Okay, that's actually all we're representing is the bonds. Sometimes you have these two lines, that means you have a double bond over there.
Like the ones inside?
Yes, the ones that are inside, right? That means it is a double bond. Everything else is a carbon. So I can go ahead and write a long chain of carbon like this. 1, 2, 3. I can just keep going. Fatty acids, sometimes these long carbohydrates are exactly like this. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 carbons. And a whole bunch of hydrogens connected to it. I can add a line over here saying there's a double bond. Okay? Yes.
So that one carbon outside, the one line outside, what's that connected to? 'Cause
This
otherwise-
one?
No, in the estrogen.
What about it?
The one line outside next to hydroxide. Top
Oh, this one?
What's that?
That's a CH3.
That's just.
The edge, every single edge, if it doesn't have anything written on it, is a carbon. Right? So that is a CH3.
So it's just.
Everything other than carbon, we have to show. So the OH, right, is not carbon, so we have to show it. Same thing over here. Right? As you can see, these are two very similar molecules, but as you guys know, estrogen is mainly common in the female hormones, and testosterone is the male hormone. Right? And the difference between them is a very minor difference, which is these double bonds mainly, and a double bond over here instead of the OH, and an extra methyl CH3 over there. Small changes make very different compounds. Yes.
So for the light, as opposed to being CH3, is that just like the carbon?
No, so you have a carbon here, and you have a carbon here.
So the point at the end is also carbon?
Yes. The point at the end is also a carbon. So if you look at the one that I drew on top, this starting point is also a carbon. But over here, this is not a carbon because it has OH on
This
it.
is the only way I can read this carbon.
Okay, but if it doesn't have anything and it's just an ending point, it also has a carbon. Okay? Make sense? Now, this is the simplified version. So when it comes to the skeletal structure, there are a few rules. They say that each vertex and each endpoint represents a single carbon. The hydrogens bonded to carbons are not drawn. We just completely ignore the hydrogens. We assume that everything is saturated with hydrogens. Double bond and triple bonds are shown with double and triple lines. Right? As you can see in these examples, instead of drawing this complicated Lewis structure, hey, I can just draw these lines. Right? And instead of drawing that complicated structure, I can just draw that. And in organic chemistry, all you're going to be dealing with are these lines. Okay? So make sure you understand what these lines mean and represent right now. I'm just introducing you guys to what organic chemistry is going to be. Okay? Does that make sense? And then also anything other than carbon, so atoms other than carbon and hydrogen are shown with their atomic symbols. For example, over here, like example Tylenol, you have this over here, acetaminophen. There's a nitrogen in the middle, you have to write it down as a nitrogen.
So it's only representing carbon and then like
Only carbons and hydrogens. The lines are only carbons and hydrogens.
so like
Anything
anything else you have to write.
else has to be written. And if there's a hydrogen connected to anything else, you also have to write it. For example, the nitrogen has a hydrogen connected to it. You have to write it. The OH that we show, right? The OH over here as well, we have to show the hydrogen connected to anything other than carbon. All the hydrogens connected to carbons, we ignore. Okay? In order to satisfy the octet rule. Right? So going back to the rule that carbon has 4 bonds, nitrogen has 3, oxygen has 2, that's how we know where the rest of the hydrogens are. Okay? So for example, if I go back to this structure over here, this carbon will have how many hydrogens? It will have 3. This carbon over here will have how many hydrogens? It already has 2 bonds, so it's going to have 2 hydrogens. What about the carbon over here?
1, 0.
It has 4 bonds already, so it's not going to have any hydrogens. Right? So you look at the number of bonds. If it adds up to 4, then it doesn't have any hydrogens.
Okay.
But like for example, this one over here,
I finally figured
It has 3, so it's gonna have 1 hydrogen. Okay. Now, here's one example. Food manufacturers sometimes add propylene glycol to packaged food to keep them moist. The condensed structure for propylene glycol is CH2OH, CHOH, CH3. Draw the structure of this compound as both the Lewis structure and the skeletal structure. So let's start off with the Lewis structure. So I have CHH, OH, CH, OH, and CH3. That look good? Okay, now let's draw the skeletal structure. Those are our 3 carbons. I have an OH over here, and I have an OH over there. And that's it. Okay? Very simplified, much easier to draw. Does that make sense? You have the 3 carbons in the middle. I drew them like this, 1, 2, 3. I have an OH connected to the central one and an OH on the left side as well. See some confused faces. You'll get the hang of it. Good question? Okay? We'll move on. That's what we have. That Lewis structure looks very confusing, but the reason why they drew it like this is to try to make it match this over here. Right, in terms of the position of the carbons. You don't have to do that. Okay. Now, as a summary, these are the 4 different ways that you can draw a Lewis or a structure of organic compounds. The regular Lewis structure that we know, the simplified Lewis structure without the lone pairs, or the condensed structure, or more commonly, the skeletal structure. Okay? Make sure you are comfortable in all 4 different types of organic structures. Now what we're going to go over are what we know as functional groups. And this is the last part. We have a few different functional groups that we're going to go over that change the properties of specific organic molecules. If you can identify these, then you can get an idea of what the properties are going to be. So small groups of atoms within a molecule that behave in a characteristic way. That is what we call a functional group. Now we have some definitions, right? First thing is a hydrocarbon. A hydrocarbon, from the name itself, it's a hydrocarbon, only hydrogen and carbon. So compounds that contain only carbon and hydrogen. And the first one that we have, I wouldn't call this a functional group, but this is the base, means a hydrocarbon that contains only single bonds. That is what we know as an alkane. Alkane, right, the emphasis on the A-N-E at the end, is a hydrocarbon that has all single bonds. These are 10 alkanes and their respective names. Now in OChem, you're going to have to memorize at least 10 of these names, but the main thing you got to memorize are the first few letters before the A and E. Meth, eth, prop, but, pent, hex, hept, oct, non, and dec. That tell you how many carbons are present in that structure. The A-N-E at the end just tells you that they're all connected to hydrogens. But the first few letters tell you how many carbons you have. So you're going from 1, 2, 3, 4, 5, all the way up to 10. Meth, eth, prop, but, pent, hex, hept, oct, non, and dec. Memorize them. A and E means it's an alkane, right? A and E, the alkane means that it is only single bonds. It means it's connected completely with hydrogens. Okay? And alkanes in general have the formula CnH2n plus 2. Right? So the number of hydrogens compared to the number of carbons is double plus 2. Right? The way you think of it, right? Keep in mind the ones at the end always have 2 extra hydrogens, and the ones in the middle all have 2 hydrogens. Right? So it's always 2n plus 2. Now, sometimes you can form isomers, as we talked about before. These are the same isomers that we drew. And if you look at the isomers of all of these, they are all exactly the same. C5H12. C5H12, C5H12. Because it's all carbon bonds. It's all single bonds, and they're not a cycle. They're not connected to itself in a ring. Because that's the next one. When you make a ring, when you make what we call a cycloalkane, you're going to reduce the number of hydrogens. So a cycloalkane is an alkane that forms a cyclic structure. For example, a ring. So you have, for example, cyclopropane, cyclobutane, cyclopentane, cyclohexane, cycloheptane, cyclooctane, all possibilities. Yes, but now the carbons are all connected. Now it's a circle. So each carbon can only have 2 bonds, 2 hydrogens. Therefore, the formula now is going to be CnH2n. Right? It's just going to be double the amount of hydrogens. Does that make sense? We good with that? So from the formula, you should be able to predict if it's an alkane or a cycloalkane, or as we're going to get into in a bit, an alkene or an alkyne, and all these different bonds. I'm going to skip this for a second. Okay? Now the second one is, instead of alkane, ane, we have ene. Alkene. An alkene means you have at least 1 double bond. So an alkene is a molecule that has at least a single double bond. For example, ethylene, right? You will see the name with E-N-E at the end. Okay? And the most we can have is a triple bond, and we call them alkyne. Right? So it's an alkyne. An alkyne is a hydrocarbon that contains at least 1 triple bond. Okay? So single bond is alkane, double is alkene, triple is alkyne. And next one we have is what we call aromatic compounds, which are similar to cyclic, but they have something extra. They are connected in a circle, but they have alternating double bonds. So for example, here you have benzene, you have double, single, double, single, double, single. And the way we draw it is going to be like that. Or, more commonly, they just put a circle in the middle, saying that it is an alternating double bond, and it keeps changing. Right, if we're here, we said it can be either these 3 or these 3, right? Top right, bottom left, left, or we can have it switch it around. But it actually keeps rotating, so we just put a circle in the middle. That circle means it is an aromatic compound, and an aromatic compound is a ring structure that contains alternating single and double bonds, and in general, it's less reactive than your usual alkenes. These are very stable compounds, and they have some very interesting attributes. Okay? Good? Alkanes, alkenes, alkynes, and aromatic rings. Those are our main 4 compounds. as you can see, sometimes these aromatic compounds have some very interesting attributes. And I emphasize this a lot. Just a small change in an atom can change the characteristics drastically. For example, this over here, right, is our ring with these specific molecules. This is known as TNT. Highly explosive. Right? Same ring, I connect different things, and you get aspirin, which cures your headache. Right? Small change of a single atoms, right? Just change a few atoms, you're going to change the properties drastically. That's why organic chemistry is all about making new compounds and testing it out, because you can come up with some weird properties that you never even expected. What's that? Aspirin. For the ones we did in the lab today, we used aspirin. That's the one that we used. Right?
It's just titration. And it's a lot easier with the blue and the pink. Did you get that one? Then it's probably going to be a little frustrating because it takes.
Yeah, so if you want the formula for alkenes, here. Right, I'll go ahead and write it over here if they don't have it. So we have the alkanes, we have alkenes, alkynes, and aromatic rings. And we said alkenes are CN, H, 2N plus 2. Now the thing is, alkenes, if I'm assuming there's only one double bond, right, because it depends on the number of double bonds, then it'll be the same as alkanes, I mean, which is CN, H, 2N, because each bond is going to reduce the hydrogens by 2. And alkynes are going to be CN, H, 2N, minus 2. Once again, that's assuming that we have only one bond or one double bond. You could have multiple. Every single bond is going to reduce the hydrogens by 2. And aromatic, it really depends on the structure. Okay? Are we good? Now the last thing that we have for today are going to be our 6 oxygen-containing functional groups. I'm not going to get into the nitrogen-containing ones. Okay? So 6 of them are what we call oxygen-containing, alcohol, ethers, aldehyde ketones, carboxylic acids, and esters. Now if you look at each of them, let's start off with the first one. We have carbon connected to an oxygen and a hydrogen. If I remove that hydrogen and I connect another carbon, it goes from an alcohol to a ether. Right? This is our alcohol. Anytime you have carbon connected to OH, we call that an alcohol. Now they usually mix very easily with water. They're aromatic compounds. Those are some examples: ethyl alcohol, isopropanol, ethyl glycol, because they have OH. Anything with OH is a alcohol. But OH connected to a carbon which has other stuff to it. If an oxygen has 2 carbons connected to it, we call them ethers. Right? We're not going to consider the reaction itself, right? But there's a reaction that goes over on how to produce the ethers. I'm not going to ask you guys about the reactions. Next is what we call the carbonyl compounds, right? A carbonyl is when you have a carbon with a double bonded oxygen. Also very different compounds. So if I have carbon with double bond oxygen and then a hydrogen, I call this an aldehyde. So these are 2 aldehydes. One of them is cinnamon aldehyde, the other one is vanillin, right? So this one is actually the cinnamon smell. I use this in my lab a lot, right? It smells very strong smell of cinnamon, and that one is a very strong smell of vanilla, right? So our fake vanilla that you use, or synthetic vanilla, is using vanillin. Okay, and this is cinnamon aldehyde. Both of them are found in the original as well. Okay, these are aldehydes. Now if I take that hydrogen and put another carbon to it, we call that a ketone. Right? So if you guys have heard ketosis and ketones in your body and anyone into fitness and all that stuff, this is what they're talking about. A carbon with a double bond oxygen connected to 2 carbons. This is acetone. Right, one example of a ketone is mint flavor. Right, you have a carbon connected to oxygen and then 2 carbons on the side of it. Right, this is mint. All flavors, organic chemistry, smells, flavors, all these interesting stuff. Okay, so these are the synthetic mint flavor compounds that we have. Then we said, so instead of now carbon, oxygen, and carbon, now we have carbon with 2 oxygens. This is our carboxylic acids. Okay, so if you have a C double bond with an O and then an OH, we have what we know as a carboxylic acid. Now most fats, fatty acids, they call them acids because of the carboxylic acid that is present at the end, and they have these long chains. So for example, olive oil, most oils are long fatty chains. But the most simple carboxylic acid is this one that we know as acidic acid, which is also known as vinegar, right? In a specific proportion. 5% of acidic acid mixed with water is what we call vinegar. Right? Once again, I said we are not going to care about the reaction too much, but as you know, it's an acid, therefore it can dissociate into its specific H+ ion. And the last one that we have for today is the ester, which also has a C double bond O and O, but this time instead of the hydrogen, it has a carbon atom. We call this an ester. So you'll get a question like this and told to find out or identify all the different functional groups. So in this case, first thing you gotta see is the ring, right? You're going to have your aromatic ring. Then you have a alcohol, you have 2 ethers, right? So it's oxygen with 2 carbons connected to it. So we have ethers. So you'll be given a molecule and told to identify the different functional groups that are present inside that specific molecule. Yes?
On the final, or you mean in general?
Final. I'm saying our final exam. That's what you're gonna get, right?
Great.
So make sure you know the 6 functional groups, right? Alcohol, ether, aldehyde, ketone, carboxylic acid, and ester. Aren't you guys grateful that you guys have a cheat sheet? Or else you would have to memorize all this, which eventually you will in organic chemistry, right? This is just an introductory course. That's why you got cheat sheets. Later on, you're gonna have to memorize all of these different types of bonds. This is what makes organic chemistry, people find it hard, because you have to memorize all these stuff. But the study itself is pretty fun and interesting. Yes?
So these different groups, they're all talking about the central carbon atom, right?
Yes. It doesn't have to be the central carbon atom. It can be any carbon atom in that molecule.
Okay, so there's different groups within a larger molecule?
Yeah. So the example that we have over here, we have ethers, we have alcohol, we have the aromatic ring. You can have every single one of these groups in one molecule.
Oh, that's great.
And that plays a different role. Right? It has a completely different characteristics. Hey guys, that's all for today, and that is all for our semester.
Get up there. Get up there.
Chem is fun. And don't worry, I'm not getting into the hard stuff there.